So now we're up on the top of the boiler and we're going to look at the steam system throughout the plant. Steam's being generated in the boiler, so now we've got a discharge valve coming out. But before we get to that, two safety valves. This is the low pressure, the 300 pound, and that's the 305 pound. This is the non-return valve, which is nothing more than a flat plate. And this valve handle crank down, push that plate right down to the seat. All we do is we open that guy up. The steam inside the drum will push the plate upwards to wherever the stop is on that, and then the steam will go down this line and head down here, keep going, and right there is a steam flow meter. And if you look at it, it's got something looks like a cable coming on the top, and that is a temperature sensor. There's an RTD that goes in there and measures the temperature of the steam. We're saturated steam, and so therefore it's going to take that temperature, put it through a lookup table, and the smart transmitter that's underneath will make compensations so that if you weren't at 250, it will compensate for the volumetric expansion of the steam below 250. Okay, so our steam is coming down here at 1725 kPa through this shedding vortex meter, and you can see that it's upside down, and it has to be that way for reasons of protection of the electronics. If it was the other way around, it was up on top, the electronics would be subjected to excessive heat and you'd get a failure on the transmitter. So this is the correct way to install it for steam. That cable I talked about when we were upstairs is the RTD sensor coming into that smart transmitter. Now, this steam is along on this line here and comes down into this header. So normally this valve would be open. This header is going to run at 1725 kilopascals. To control it at 1725, we're actually going to change the firing rate on the boiler, so the fuel flow, airflow. So over here at the end is a pressure transmitter, and this pressure transmitter is looking at that 1725 header pressure. It goes to the controller, the plant master controller in the DCS, and the output of the plant master goes to a boiler master and then goes to the fuel flow and airflow controls to raise or lower the firing rate to maintain this header pressure constant. While we're standing here, we also have, sitting on the end of this, a throttling calorimeter. Now what the throttling calorimeter does is it actually can measure the quality of the steam. And there'll be another video coming up where in fact we'll go through how to do that. But mechanically it's sitting here, and there's a tube that goes down inside the line itself and extends more than halfway down, a whole bunch of holes in it. So it's averaging the steam to give you a good quality sample. Comes up, goes through an orifice that's sitting here, so you open this valve, goes through this orifice, and blasts away to atmosphere. It basically goes down into that trap down in there. You then measure the temperature, and then you look up on a graph to see what temperature is this expanded steam got to, and that's the thermal expansion of it, and that will tell you what the percentage of water content in the steam is. Out of a water tube boiler like that Nebraska, the design spec says that you're going to be running about 0.5%. So that means that your steam is actually running at 99.5% quality, and you got about 0.5% water in there. So now, middle of the header, we've got steam coming up through a block valve, which is open right now. Comes up, goes over to 150 pound header. If I follow the line up with my laser, okay, you'll see the line actually swings. It goes around, it goes back, and then it goes to another steam flow meter where my laser is pointing right now. And it's an identical meter to the one that was measuring the boiler outlet, except that this one is not compensated. So what you can do is that when you look at the steam flow coming off the boiler, if the boiler pressure in that header was only running at 200 psi or 1379 kilopascal, then what would happen is the steam has dropped in pressure, it's expanded in volume. Go to the steam tables and look and see what is the specific volume of the steam at 200 psi, and then compare that to the specific volume of steam at 250 psi. You would discover that there's a difference. It's got less volume to it. When you look at the factor between the two, you then take what the steam flow is on that flow meter that's not compensated up there. You take that guy and multiply it by the factor difference between the two. You would discover when this guy was showing maybe 2,000 kilograms of steam coming out, this guy's sitting at 2,500. And it's due to the fact that the volume of the steam is expanded. We could have put compensation on both, but we wanted to do this intentionally to show that unless you're running at the pressure that the meter was designed to run at, you're going to have errors. And the moment that we bring this pressure up to 250 psi or 1725 kilopascal, that meter agrees with that meter. The two meters perfectly match one another. Obviously they're moving a little bit, but they're very much in sync with each other. Okay, so up on this upper deck, which is at the front of the boiler room, looking out the windows, we've got a number of junction boxes. This is device net, where all of the variable speed drives for downstairs for the pump, and also the signals that's going up to the fans that we saw on the roof. This one over here is foundation field bus, because we've got some foundation field bus stuff running here. Everything that's in the orange cable is SP50 foundation field bus. Things like that Foxborough steam flow meter that's right there that is measuring the steam flow going into the instrumentation lab. So the boiler house knows exactly how much the instrumentation lab is taking by that flow meter. More foundation field bus stuff sitting in here, and more foundation field bus stuff sitting in here. Okay, so there's a number of junction boxes up here, and then this junction box is running 4 to 20 milliamp because there's a number of 4 to 20 milliamp signals. Okay, and then back over here, and this is what I wanted to deal with. We've got steam flow coming up that we talked about, and there is the second steam flow meter that is measuring the high pressure steam. And it could be at 1725, or if we're running the boiler at 200 psi, this should be down at 1379. This guy does not have a temperature compensator. There's a plug sitting in where that would go. Now, the steam comes along, and I mentioned downstairs, when we were looking at the screen, that there was two valves, and here they are. There's 2404A, running foundation field bus, and then this one is 2404B, a larger valve, the smaller valve. So this valve goes to 0 to 70% open, this valve goes to 0 to 90% open. And the minute you take this over 70%, the noise level comes up way up, like it's well over 75 dB, and it starts climbing exponentially, which you expect, okay, with noise. And yet this valve down in here, as I say, by the time I get over 70%, there's already so much noise in this steam plant that you're not going to hear. And so this was a real annoyance to some of the people that were here, because this valve was running up in the 80% region, and it was just screaming in here, and yet there wasn't very much load and not much noise coming from the boilers. And so we changed the ranges, so this is 0 to 70, this one is 0 to 90. Okay, so the pressure reducing valves between the 250 pound header and the 150 pound header are actually split range. There's two of them in here, A and B, these two valves, and they're ranged such that for a 0 to 100% signal coming in from the controller that's controlling the pressure, 0 to 100 moves valve A from 0 to 70% open, and valve A is the larger of the two valves, and then valve B, for that same 0 to 100% signal, moves valve B from 0 to 90% open. Cut that off, that was wrong. Okay.
Let's repeat.
Okay, so these are split range valves, two of them, And this is the splitter block that actually splits them. So the output of the controller goes 0 to 100%. And as it does, the very first valve, the little valve, goes 0 to 70% open. And what happens with that little valve is that anything above 70% open is where we create a lot of noise, because these valves are E-body valves. They do not have whisper trims in them. And we intentionally did this so that we could prove that the most of the noise is generated at the top 30% of opening. The second valve, which is a larger valve, runs 0 to 90% open, just in case we need extra steam. And we're already up at such a high firing rate that the noise level, you can't hear it in this place. Okay? That's okay. So this is coming from the two split range valves. This is the steam coming down, which has now been reduced down to 1035 kPa or 150 psi. Comes into this header at 1035 or 150 psi. And then there's takeoffs going everywhere. Steam coming in from the view boiler. Steam going out to the turbine feed water pump. You remember earlier that we talked about a turbine-driven feed water pump. Steam to the deaerator that we looked at upstairs. And then the instrumentation lab is way over here on this side. And this goes to the 15-pound header. This guy's normally closed, unless we're running a turbine. Steam comes out of this line. This valve is wide open, and it goes up, I'm sorry. So steam goes up, there's a flow meter right there, and that's an accelebar. And that accelebar is actually a machine venturi with a pitot tube inside it. And you're going to find this hard to believe, but it's actually got a 60-to-1 turn down ratio. And we proved it. Orifice plates, flow nozzles, venturis are 3-to-1 or 4-to-1 at best. This thing is running 60-to-1 guaranteed, and it works. It's got a smart mass flow meter measuring the temperature and the pressure, and then it goes through a reducing valve, which is up there, that great big thing that's up at the top, and knocks the pressure from 150 down to 15 or 103 kPa. The steam comes out of that valve, and it's actually superheated at this point in time, and we've actually got a desuperheater. So that little valve there is actually adding water from a sweet water condenser into the line, and there's a spray nozzle that goes down inside the line and sprays the steam. And then the steam goes all the way down here, and I don't know whether my laser is going to point this out. It's a long ways away. Right up above us there should be a temperature sensor. You can't see the cable. There's the cable right there. I don't know whether you can see it. That's the RTD cable coming off. Just upstream of it with the drip leg. So any condensate, any water, deaerated or steam that we put in there, the water that we put in, we try and drop the temperature. If it hasn't gone to steam, it'll drop out on that steam trap. The line loops around, and it goes all the way back to the load condenser. Did it yesterday. There is the 103 steam, and it's going that way. And there it is there, coming in from the pressure reducing valve, goes into the load condenser here, gets condensed, the condensate, then it comes out the bottom. Here, in a sump. We actually are measuring the temperature of it and measuring the level of it. Okay, let's